Welcome to the start of Chapter 9. We're going to start looking at moles again. No, not the thing on your aunt's face. This mole, the chemistry mole. Before we do that, the first thing I want to look at is a balanced chemical equation and exactly what that tells us. Well, the first thing that it tells us is that we need one molecule. One molecule. Yeah, molecule. Like a compound, it's different from a mole, but a molecule. So this says we need one molecule of carbon monoxide to react with two molecules of hydrogen to make one molecule of methanol. All right, well that's easy enough. But what happens if I take each one of those coefficients and I multiply it by, say, 12? Will that change the ratios? Nope, not at all. So how about if I multiply each one of those coefficients by, say, 6.022 times 10 to the 23rd? Will that change the ratios? Nope, it doesn't. So what that allows us to do is say, hey, instead of one molecule of carbon monoxide, I have 1 mole of carbon monoxide. Now, of course, we don't actually write the 1 there, but we know it's there. And it allows us to say, hey, we have 2 moles of hydrogen and 1 mole, I'll put the 1 there for you, of methanol. Now, this allows us to set up mole ratios. And what this means is that these chemicals, this one, and this one, are all related to each other based on mole ratios. So what we're going to look at first with the mole ratios is the same reaction I've been using this whole time. But one of the things I wanted to show you was that this is carbon monoxide, comes out of the back of your car, and hydrogen gas, which is what blew up the Hindenburg, gives us methanol. I just thought that was kind of interesting. And if you look at the actual chemicals, carbon monoxide, hydrogen gas, gives us methanol. And what type of chemical reaction is this? For an extra credit point, write that down. Because each one of these chemicals are related by moles, we can write mole ratios. And now a mole ratio, you should know, is simply a conversion factor. These are conversion factors. They allow us to convert from 1 mole of a substance to another mole of a substance. We're going to go from moles of one substance to moles of another. So I should put mole A here to mole B here. So in this problem, I can say that for every 1 mole of carbon monoxide, because there's a 1 right there, I happen to have 2 moles of hydrogen. I can also say that for every 2 moles of hydrogen, I have 1 mole of carbon monoxide. These are conversion factors. I could say for 1 mole of carbon monoxide, I have 1 mole of methanol. Or I could say for every 2 moles of hydrogen, you make 1 mole of methanol. All of these mole ratios are totally possible. Let's look at another chemical equation for mole ratios. Now this one's interesting. If you take lithium hydroxide, which is created by putting lithium metal in water, and carbon dioxide, which we exhale and comes out of smokestacks, you end up with lithium carbonate, which is an essential ingredient medicine for those with bipolar disorder, and water. Lithium hydroxide's an ionic compound, looks like that. Carbon dioxide's covalent. Lithium carbonate is ionic. This structure, the 3 structure right here, this is the carbonate ion, right? CO3, 2 negative, so we need 2 of these lithium ions, and water. Let's look at the mole ratios on this chemical equation. Smooth, Kate. All right, so how many moles of lithium hydroxide to how many moles of carbon dioxide? Make a guess. Okay, so we have 2 moles of lithium hydroxide for 1 mole of carbon dioxide. Now try this one. 2 moles of lithium hydroxide for every 1 mole of lithium carbonate. Try this one. What would those numbers be? 2 to 1. And this one? Again, where are we getting these numbers? From the balanced chemical equation. Try this one. These things are going to allow us to convert from one substance in a balanced chemical equation to another. So what are the numbers going to be for this one? Nice job. Now that you can recognize a mole ratio using the same balanced equation, remember the equation has to be balanced. The question is, if we have 5 moles of carbon monoxide, how many moles of hydrogen am I going to need to completely react all of the carbon monoxide and make it go away? So this actually becomes a conversion problem. We're going to start with what's given, which in this case was 5 moles of carbon monoxide, so that's going to go right there. Well, if moles of carbon monoxide's there, that unit must go down there, like that. 1 mole of carbon monoxide. And what we're trying to get to now is 2 moles of hydrogen. That's what it's asking us for. Do not get lazy and drop these off, because 1 mole of carbon monoxide can only be canceled if you have moles of carbon monoxide here. And I see students all the time, they want to drop it off because they're lazy, they don't want to write all of that, but then mistakes are made. Trust me when I say, you must, if you don't want to make mistakes, write down the name of the substance next to the word mole. Now you simply can do the math and you end up with 10 moles of H2. And are sig figs correct? Yes, they are. All right, what number of moles is produced decomposing 5.8 moles of water? Well, the first thing you're going to have to do is balance the equation. So let's put a 2 here and a 2 here, which balances the equation. And then we have 5.8 moles. I like to write what's given directly under the substance, and then put our question mark of moles underneath the other substance. That allows us to see what we have and where we're going. So let's start off with what's given. We have 5.8 moles of water. Do not forget that when you do your conversion, when you bring your moles of water down here, make sure you write H2O. Moles will only cancel if it's the same moles of substance. What are we converting to? We're converting to moles of oxygen. What numbers will go in here? Well, because there's a coefficient of 2, this becomes 2, and there's a coefficient of 1, so this becomes 1. Now you're ready to pick up your handy-dandy calculators. And we end up with 2.9 moles of oxygen. And do we have the correct number of sig figs? Well, there's 2 there. There's 2 in our answer. Awesome. We're done with this problem. There's more. Take a minute, read through this problem, and actually try this one on your own. See if you can do it. Well, first you better balance that equation. Okay, so carbons are good, hydrogens are now good, so put a 2 there. Oxygens are good. We have 7.4 moles of methane, so I like to put that right underneath the substance we have. And it says what moles of oxygen gas is required to completely burn all of the methane. We want all 7.4 moles of methane to go away. Okay, so 7.4 moles of methane. I'm going to draw the handy little line thing. Remember, if moles of methane's here, moles of methane, don't drop the substance, goes down there. Then moles of oxygen goes up there. Put in your coefficients, so 1 mole of methane for every 2 moles of oxygen. Now you're ready to calculate. Oh, by the way, for an extra credit point, tell me what kind of chemical reaction this one is. So we end up with 14.8 moles of O2. Are our sig figs correct? Well, here we have 2 sig figs, so our final answer should be 15 moles of O2. Let's try another one. Go ahead and pause the video, see if you can do this problem on your own. Okay, well, yeah, it's got to be balanced. So we need a 2 and a 2. Now that's balanced. Okay, so we have 2.6 moles of oxygen. 2.6 moles of oxygen. And we want to know how much carbon dioxide is going to be produced. This says with excess methane. And what the word excess methane means, you have so much of this that you are never going to run out. You have so much more methane than you have oxygen, you don't even have to worry about it. But that's what those words mean. Way much. Okay, so let's start with the 2.6 moles of oxygen. And if moles of oxygen's here, it's got to go down there. And we're converting to moles of CO2. And the coefficients say for every 2 moles of oxygen, we make 1 mole of carbon dioxide. So that gives us 1.3 moles of CO2. Because look, see, those cancel. Are sig figs correct? Well, we have 2.6. That's 2 sig figs. We have 2 in our answer. Awesome. Another problem on the way. Okay, so the problem is yours. Choice to do or not. You can do this one and let me know how you did. It's worth extra points. All right, up next we are actually going to get into real stoichiometry. This is where we really are going to be able to predict how many grams of a reactant, take it to moles of that same reactant. So we'll do grams of A to moles of A, and then we can convert to moles of B and find out our grams of product.